In this problem, we'll be looking at a slightly more complex circuit and finding the currents and voltages in that. In this case, we have a multi-loop circuit because, as you can see, there is more than one loop of wire in the circuit, so it's generally called a multi-loop circuit. Now, whenever I do these problems, again, there's a fairly set way of doing it. I have to find the currents, and the first thing I'm going to do is label the currents. Now, currents always begin and end on junctions. And here are the two junctions. So in any stretch between those two, it has the same current. I'll label the bottom current. I'm going to guess that it goes this way. Again, using the fact that it tends to cross through batteries in this direction, which I tend to phrase as from the negative to the positive, which means inside of the battery. If you were thinking about it externally, then it typically flows from the positive to the negative on the outside, but internally, and I'm not trying to indicate what actually happens on the inside of the battery, just trying to label a direction. If I mean to the left on this picture, I am referring to that as from the negative to the positive. That's all I'm saying. But I'll call this current I1. I'm going to assume that this current continues going around here clockwise for what I'll call the second current. And then I'm just going to say the third one goes to the left between these two junctions. And I'm going to call that one I3. Now, when I've done this, the reason I've chosen these two currents is I want to show you what happens when one of them is guessed in the wrong direction. I already know the answer here. But we'll just go through and say, if you don't know what direction it is, you can just guess. Here I've guessed the directions of the current. So the question is going to be, do I have enough information to solve for these three? Well, what do I need? How many unknowns am I looking for? Well, I have three currents, I1, I2, I3. All of the resistances are known, and the EMF is known. So all I have left to find is three currents, so there's only three unknowns. Which means I'm going to need three equations. Well, how many equations can I do? I have two junctions in this circuit. That means I can have one equation, because you always do one less than the total number of junctions. So I'm going to say the junction equations are only going to give me one. So I'm going to need two loops in order to solve this. Now note, there's actually three different loops you can make on here. I could go all the way around the big loop. I could go just on the little bottom part and do that as a loop. Or I could do this top part and do it as a loop. So there's three options, but I only need two of them. Which is also good because, as you might be able to see, if I've say done the big one already and the bottom one, I've used all the circuit elements. I've already had them all inside of one equation. So I don't have necessarily any more that I can do. So at most, I actually have only two loop equations I can do. So luckily I've designed this problem so you have exactly the right number of equations to solve for the unknowns that you need. So let's start writing down these equations so we can do some yummy algebra. Okay, junction number one, that's the only junction rule. I'll choose that to be the left one right here. Okay, what does this say? Well, it says the currents coming in equal the currents coming out. What is coming in? I1 is coming in. I2 is coming in. Oh, sorry, I3 is coming in. So therefore, I1 plus I3 equals the current coming out, which is just I2. Okay, so that's one equation. What about a loop equation? Let's go through and do loops. Well, there's different loops I can do. Let's do it this way. I'm going to do a loop that is just the bottom here, because I want to show you what happens if you go against the current. So let's say I go start at here. I'm going to call this L1 for the start, for the first loop equation that I'm going to draw. I'm going to start here, and then I'm going to move through this. I'm going to move in this direction. I'll first hit the battery, and then the battery, I'm going to cross the battery in the direction of the current. So my voltage change, call this L1 for my first loop equation, is going to be plus E. And I'm going to use a symbol instead of the actually listing the values because it's going to be a lot simpler. Okay, so I went with it, so it was a positive, and then I went up to here. Now I'm going to go this path to get back to the beginning. So I'll go through the middle. Now I'm going to go through a resistor, R1. But I'm going to go through it backwards. The current runs to the left, at least I think it does, and I'm going through it to the right. So therefore, I'm going to actually gain voltage. Because physically, the current loses voltage as it goes through. It's lower voltage over here than it is over here if this current is in the right direction. And so if I go the other direction, I go from the low to high voltage side, meaning I should add IR. And again, I want to make sure I have the correct currents and the correct resistance. So the current through that resistor is I3. So I'm going to write this as I3, and the resistance here is 1. So that's R1. Then I go through the second resistor, same story. I'm going against the current, so I add I3 R2. I then hit this junction, head down to the start, get to there without meeting any circuit elements. Now I've completed a full loop. All my changes must sum to 0, so I say that this equals 0. And my second loop rule, I'm going to do, let's do this one right here. Okay, I'll start from this point here. So I'll say this is L2 start. Go up, and just go in the direction of the current in all these cases. It'll be a little bit easier. So they'll all be subtracting IR. First I hit this third resistor. It has current number 2 flowing through it. So this is minus I2 R3. Then I go through the fourth resistor. That's minus I2 R4, all minuses because I'm continuing in the direction of the current. Going through this one, I have minus I2 R5. Now I'm going to go take a left, go through the middle. I'm now along going in the direction of current 3 through resistor number 2. So I have minus I3 R2 and minus I3 R1 for this one. Now I've gotten back to the original spot, so all these changes must sum to 0. And these are my 3 equations I must solve for. Okay, now let's think about how do I solve this? Well, here's a problem-solving strategy. First, pick an equation where you only have one unknown. In this case, only the middle equation has I3 as an unknown. I'm going to solve this equation for I3. Then it'll be a known variable. Let's look for an equation that only has one more unknown. That'll be this one down here. This only has currents 2 and 3. And therefore, once I plug in with 3, I can solve for 2. Then I'll know 2 and 3. I'm going to go solve an equation that only has 1 in it. So I'll go up to this equation. Okay, so I'll now know 3, I'll know 2, and I can solve for 1. And those will be my 3 currents. So in the next slide, I'm just going to go through and do the algebra to solve for these 3 currents. So as I I'll flip back and forth between them to show which ones I'm talking about. So let's solve for L1. Let's look over here. I can pull out a common factor of I3, and that'll be the first thing I do. So I say I3 times R1 plus R2 plus E equals 0. Now I'm going to solve for I3 moving this to the other side and dividing, and I get this. I3 equals the EMF over R1 minus plus R2. There's a minus sign because I moved E to the other side, which equals to negative 9 volts, negative because the negative sign already present in front, plus, and I'll just add these together, 20 ohms. So I get this negative 0.45 amps, so 4, like we had last time. The negative means that I guessed the wrong direction, that the current is actually to the right, but we can proceed with all this math the same and just know that I would have to flip the direction of 3 when I list it at the end. So here's one current. Now let's do the second loop equation. And again, I have a common factor of I2 that I can pull out, as well as I3, so I'm going to make this even simpler and write this as minus I2 times R3 plus R4 plus R5 minus I3 times R1 plus R2. And that'll equal to 0. So if I solve for I2, I move these to the other side, and I divide by negative R1 plus R2 plus R3, leading to I2 is now equal to, if I move this over, it becomes positive. I'm going to subtract by a negative number. Overall, this is now negative I3 R1 plus R2 over R3 plus R4 plus R5, which is minus 0.45 amps. Excuse me. That's the value. I still have a negative sign left over. I'm just using the negative, brought it down here, times 20 ohms divided by 7 plus 8 plus 12. And so this is 27 ohms overall, giving me 0.33 amps. Okay? And the two negative sides, so this is, yes, this is not a volt, this is a check mark. So I've checked off that I now have two different currents. And the last one I am going to use is the junction rule. The junction rule equation was that I1 plus I3 equals I2. I'm going to solve for I1. That's equal to just I2 minus I3, which means it is 0.33 minus negative 0.45 amps. Or in other words, this is 0.78 amps. So now we have the three currents, I1, I2, I3. The next step is going to be, sorry, I realize I now have this capture on here. I'll minimize that.